But we'll head up. We've got a few more talks to get through, so we'll get on with the talks for this afternoon. So next up, we've got Danon, who's recently moved to Bristol University, and he's going to be talking about their work on household bubbles and COVID-19 transmission, insights from percolation theory. So I'll hand over to you, Leon.
Hi, everybody. Can you hear me and see the screen?
Yeah, we can hear you.
Okay, and hopefully just the presentation and none of the background stuff. So this is thanks very much for organising. This is really great. What a fantastic day that you put together. It's really amazing to see all the work that's been done. So when I'll be talking about household bubbles, some of the work that we did last year on household bubbles and transmission, and what we can sort of understand from network theory. My background, as many of you know, is in statistical physics, and this is work that I've done with some statistical physics friends of mine and Ellen Brooks Pollock. I guess a lot of this has been covered in the previous talks. The things that we've done in the Southwest and the Southwest axis of Juniper has been some transmission modelling, but really I thought for this talk it might be interesting just to think about the network side of things a bit more closely. This is just a list of the things that we've sort of contributed over the past few months. So what is household bubbling? I guess I didn't, and now I can't go through. Oh, yes, I can. Oh, great. Okay, so what do we mean by household bubbles? So this is an idea that was used to try and kind of relax some of the massive social distancing impositions that were made to control the virus. It was used in Belgium and New Zealand to allow sort of mixing and relieve some of the social pressure, but still contain the epidemic within small patches of the population. And that essentially involves joining households into bubbles of that are exclusive. So they kind of join together and they don't really have that many links outside, but there's still some social interaction between people within a couple of households or 3 households or whatever, which is what we're going to be talking about here. Why are we interested in this? Well, it's one of the major implications of the lockdown has been the impact on mental health and therefore physical health, especially during the height of it. This was, it wasn't particularly pleasant, especially for people that were living alone. They were much more affected, and there's a piece of work that was done in the ALSPAC cohort, which is a longitudinal study of people in the Southwest, who looked at the kind of the levels of depression in a whole bunch of people. And the highlighted part of this is that people living alone were experiencing much more acute symptoms of depression, particularly because of lockdown, during lockdown. So the question really is, can we increase that social support? And can we increase the number of social interactions to individuals like that without a massive increase in transmission of disease and elsewhere, really? So that's what we set out to do. And hopefully I can go to the next slide. We looked at this specifically in the UK. We looked at the household structure. This is a plot of the distribution of household sizes within the UK, which is coming from the UK Office of National Statistics with some help from Joe Hilton. And it basically shows that the vast majority of households are less than a size of 3. So they're smaller than 3 people contained in a single household. And about 30% of those households are households of size 1, so people living alone, which are, from a mental health perspective, quite vulnerable. the basic idea of the household bubbling and the way that we approached it was to join these households up pretty much at random and then study the topology of the network that we've made. So we're making quite strong assumptions about how these households interact. And what we essentially do is we make a household that has, here I'm showing 3 different households of size 2. Can you see my pointer? This is the household of, the yellow one is a household of size 2. The blue one is a household of size 3, the red one is a household of size 4, and so on. And we make the assumption that each member of a household makes a single link to outside of their household. And those links are distributed across the entire network at random. So these kind of edges, these kind of the edges are connected up at random across the network. And then the bubbling, so this is kind of the baseline network on the left here, and then we model bubbling by merging households according to the strategies, which I'll go on to define in a minute. But here I'm just showing the merging of the yellow and blue into the green household, which goes from having 2 households, one of size 2 and one of size 3, into a single household of size 5 with a degree of 5. Degree meaning the number of external connections. The traditional network terminology of degree. And that's the fundamental idea, which we'll be using throughout the rest of this, this analysis. Okay. Then we look at what is known as link percolation. That means that on this substrate network that I've defined in this way, we essentially pretend that none of the links exist, and we add them with a certain probability. If the probability is 1, the entire network is represented. The entire network of link is represented. As we reduce P, this probability of a link existing, the network starts breaking up. And there's some very nice theory coming from statistical physics, which defines the threshold, the percolation threshold, at which point the network breaks up into lots and lots of small components. Above the threshold, a giant component appears, which dominates the network. Basically, it's about the size of the same order as the size of the whole network. And below that, you have lots and lots of disconnected components, all of which are relatively small. The percolation threshold, PC, is given by this expression here of the average number of links divided by the average squared minus the average number again. And we're particularly interested at which point this percolation threshold appears under different bubbling assumptions. So this is what we did. We considered multiple bubbling scenarios. We looked at 2 bubbles, and that's defined as all households would join together at random, essentially in pairs, and that would create a bubble of 2 households. 3 bubbles is very similar to 2 bubbles, so you have all households joining together with 2 other households, making joining 3 households together, again chosen at random. And then we looked at these strategies which particularly consider individuals, these vulnerable individuals. So all single person households would join together with another single person household. So this is the 1+1 strategy. And the 1+n strategy is all single person households join together with any household from the population. And 2+n is just an extension of that, where we look at single person households and 2-person households joining together in a bubble. Okay. So we then perform a percolation simulation and compare it to the theory. But a percolation simulation essentially is removing the links from this network, or adding them if you start off with a network with no with no links in it, and then looking for the phase transition, looking for PC, this critical threshold at which the network becomes connected. And in figure A here, I'm showing the giant component, the size of the largest component in the network, and how that behaves as you increase P. The location at which this starts to take off is close to the percolation threshold. And this has a direct analogy to the behavior of the final epidemic size and R. So this looks exactly like R being across the x-axis and the final size of an epidemic on the y-axis. There's another way of finding the percolation threshold, and that is to look for the mean size of the components other than the giant components. And that's easier to identify because it's a very abrupt change in this profile. So that's in figure B. And I'm showing all of these for some of the different strategies that I was talking about in the previous slide. So 1+1 bubbles, 1+n, 2 bubbles, 3 bubbles, and so on. What I'm not showing is actually that the theory agrees incredibly well with where these percolation thresholds lie. They're basically in the middle of these simulation distributions. And we're assessing really how fragile the network topology is for different scenarios. What this means is that certain networks are much more fragile. The further to the right in these graphs that PC lies, that the percolation threshold lies, the more fragile the network is, and essentially the better for controlling the epidemic. The easier it is to control the epidemic in such a scenario. So what that's telling us is that the no bubbles, so each household on its own is the best. The 1+1 bubbling strategy, where you're joining up individuals together in households, is the second best, and so on. More or less intuitively, as you would expect, that joining up households of size 3 into bubbles of joining 3 households together is the worst of the lot. So this was work done during the first lockdown, really, and it kind of came back a few months later when we started thinking about Christmas. So over Christmas, the question was again posed as to what happens if you allow multiple households to join together over the Christmas period. And we thought we could use the same methodology to do the same kind of analysis and see what's better and what's worse. Over Christmas, there was some surveying done of what people were intending to do over Christmas. And we thought that a plausible best case of what might happen over Christmas is that 33% of the households would form a bubble, half of which are 2 bubbles and half of which are 3 bubbles. A kind of intermediate, plausible, reasonable case would be that about half of households form a bubble. And the worst case would be that 75% of households would form a bubble, half of which 2 bubbles and half are 3 bubbles. It seemed to us to make sense. And as you might expect, the best case is the best, the reasonable case is in the middle, and the worst case is the worst in this analysis, which makes us think that the method is giving us something that's sensible, but also kind of provides a way of really analyzing this kind of quantitatively. Okay. So if we plot all of these strategies and we compare them all to each other, we get a hierarchy of what's best and what's not as good. And I think it's quite comforting that the bubbling strategies that were actually implemented, that we were actually thinking about, showed up at the top of this graph. The Christmas strategies kind of appeared in the middle of this graph, so not quite as good. And some of the ones that weren't particularly supported were the worst. We extended this to try and understand the effect of bubbling on the household reproduction number in a very straightforward, sort of simple way, to basically have a look at the expected number of infections that you might get within a household of size H, and we multiply that by the proportion of households of size H to get a kind of household reproduction number. What this graph shows is how that number scales with the number of outside infections per person. And what you can see from this is that under certain bubbling strategies, the gradient of how this scales is different. And it's different because the underlying substrate network is different. So following the same hierarchy of importance that we saw in the previous graph, the no bubbles, so all households behaving separately, has the lowest gradient of this line. So the household reproduction number doesn't go up as quickly, whereas the bubbles where you're joining up three households into a single bubble is the worst, the worst strategy. So that was kind of a nice supporting piece of analysis that we could do with this approach. Okay, the implications of this work were that, you know, support bubbles were supported in some way. They were essentially allowed between solo households and single parent households and so on. Over Christmas, this got quite a lot of coverage in the media, and these kind of plausible, reasonable worst case scenarios were taken into account, really. There's the DOI, the link to the bubbling paper, which is, well, available, and hopefully we'll have some code soon so that people can look at it and play around with it and hopefully join in with us. So just to conclude, I guess this highlights that percolation theory, even though quite old, is still quite powerful. An analysis of the collective behavior of networks is, you know, is a useful tool for analyzing how things are going to progress. The epidemic characteristics we're really simplifying this. We're making it, we're looking at sort of capturing it through just the network topology that we've used here. But there is scope for developing this quite a bit. And there's certainly scope for making it more realistic. We've kind of ignored household composition by age, which we ought to really build into the next part of this work. There's also some work to be done on making the mixing between households spatial and have localized mixing. That's obviously going to have an implication on how the network looks, and its percolation threshold behavior. And also some work on interpreting this work further. So what are the implications on this on protection, on whether it's vaccination or natural infection? And once we get rid of the large parts of this epidemic, what are the implications for the endemic states of COVID and actually all other viruses? And this kind of work can help us do all of that, hopefully. So I'll end there. I'll thank all of you and our funders for listening.
Great, thanks, Leon. So there's a couple of questions that have come in. So first of all, Jordan has a question. How might altering time dependency assumptions relating to transmission affect your results?
So in this very simple analysis, time dependence is kind of, we've kind of ignored it to a large degree, but it would essentially be built into P, into the probability of a link existing between households, which can be varied. There's no reason why it can't be varied, and we could look at we could look at the sizes of components over time. So it's entirely possible.
Great. So there are a couple more questions, but in the interest of time, I think either Leon can answer those question or type answers, or we'll come back to them later. So thank you very much, Leon. And